So, linear approximation and differentials. Okay, there was a reason why I had you write a tangent line equation this morning for your problem of the day. Okay. Linear approximation means the same thing as write a tangent line equation. Okay. With linear approximation, we're just going to use the tangent line to approximate a value. Okay. So here I have a picture. We have a red curve, and this blue line is our tangent line, right? Okay. Let's talk about how do we find the slope of this tangent line? The derivative. Okay. So if we are going to write the equation of a line, this is how we write it. Since we're using calculus to write it, we know our slope is the derivative at that value. Okay. So if we're going to use this to approximate a y value, okay, we can just rewrite it to where this gets added to the other side, and that's all that this is right here. Okay. I don't know if you really need to write this down because you know how to write the equation of a tangent line. But what we're going to do with linear approximation is take this tangent line equation and use it to approximate a value on the curve. Okay. Why would we do something like this? Okay. In the case of we don't have our calculator, okay, there are times where plugging a number into a function is not always nice. Okay, like taking the square root of 2.5. Okay, we can't just like do that with a snap of our finger without a calculator, right? But what we can do is, let's say that we want to approximate this y value right here. What we can do is just move along the tangent line and use that x value to figure out the value that would be on the tangent line, but pretty darn close to being the y value on the curve. Does that make sense? Okay. So we'll move along the tangent line to approximate a value on the curve, but we know that it's not going to be the exact value, but it should be close. The closer we stay to the point where we found our slope, the closer we will be to the actual y value, right? The further we get out on the tangent line, the further our y value will actually be from the real thing. We call it linear approximation because we're using the tangent line to approximate our value. See how that all comes together? All right, so let's see this in action. Find the linear approximation of square root of x at x equals 4. Okay, basically I'm asking you to write the tangent line equation at x equals 4. Okay, so there's a couple things that we need. What's one thing that we need, Alex? We're going to write a tangent line. We need the y value. If our x value is 4, what is our y value? 2. What else do we need? We need slope. And how are we going to find slope, Josh? Derivative of the square root of x. How do we find it, Joe? Okay. So our slope at 4 when we plug in 4 to our derivative, what is our slope? What was that, Cole?
1/4.
1/4. Okay. So our tangent line equation would be y minus y equals slope times x minus x. And since we're going to use this line to approximate a value, let's go ahead and add that 2 over. It doesn't matter if you add it in the front or the back, right? Addition is commutative. Okay? All right, so what are we going to do with this? I want us to estimate the value of the square root of 4.02. Now I know that we can punch this in our calculator, but let's say we don't have a calculator. Okay, that's the point of this. Okay, the square root of 4.02 is not something that we want to just do without a calculator. But what we can do is we can use this tangent line equation to approximate the y value of the square root of 4.02. So I'm going to go ahead and rewrite our tangent line equation here. Okay. So if we want to approximate the square root of 4.02, and we use the square root of 4 to write this tangent line equation, what we can do is just plug in x is 4.02 into our tangent line equation. Okay. Remember, our function was square root of x, so 4.02, since it's under the radical, is our x value. All right, 4.02 minus 4. And what happens when we take 2 100ths and divide it by 4? It becomes 5 thousandths. So what this means is the square root of 4.02 is approximately 2.005. All of that without a calculator. Questions? Okay, now let's think about the picture here. Well, how about this? Before I draw it up here, I'd like you to have a 30-second conversation with your pod. Do you think this estimate is too high or too low? Is 4.005, 2.005 higher or lower than the actual value of the square root of 4.02? 1, 2, 3, go. Don't grab your calculator, just think about it.
Actually, it's lower.
All right, pod 2, what do you have to say? And why do you think that?
Well, the graph should be increasing in the beginning, like at a faster pace, and then it starts slowing down. So if you have a higher value after the value you get in, then it will have a lesser slope tangent.
Okay, what's a way to describe that? Okay, concave down would be a more concise way to describe that, right? Our graph is concave down, which means our tangent line will sit above the curve. Therefore, this approximation right here is going to be an over approximation because we use the tangent line sitting above the curve to approximate. Okay. That will be a very popular question throughout the course of this class. Okay, so make sure you keep that in mind. Okay, if we're talking about a tangent line approximating our value, if we think about the concavity, concave up or concave down, we can think about where that tangent line is sitting, above or below our curve. Okay, so we are essentially going to be doing the same thing using a tangent line for approximation. Yeah, that's what I really funny about tangent line now.
Oh, that's right.
Huh?
That's right.
Okay. We're going to use the tangent line to approximate our values, but it's going to look different. Okay. Let me see if I can. I need to figure out how I get this to dual page here. Okay, so I have kind of this big messy picture up here. We have this blue curve and a pink tangent line. Okay, and we are going to approximate the value using the tangent line, and you'll notice that I'm denoting that with change in x. Okay, that's how much further from x we're going to use our tangent line. Okay, change in x is that dx or delta x. Okay, so go ahead and write that down. Delta x and dx both mean change in x. How far away are we from the original x value? Now, there is a difference between delta y and dy. Delta y, as you can see in this picture right here, that is the actual change in the function from x to delta x. Okay? If we move delta x from our x value, delta y is the actual change in height. Oh, how did that not get saved? This should be that. From x to x plus delta x. Okay. Now, I want you to look at the picture. dy. That is the change in y on what part of our picture? Here's dy. Where's that point? On the tangent line. Okay? So dy is the change in y on the tangent line. there are three ways that we write derivatives, right? One of them is dy dx, and another is f prime of x. What we can do with this concept of dx, dy, change in x, change in y, is we can rewrite f prime of x equals dy dx to be this. dy equals f prime of x dx. We're essentially multiplying that dx over to be with f prime. You making a napkin? Do you need a napkin? Do you need a napkin? Okay. Okay, this seems obvious, but if there is no change in x, then dy and delta y would be the same. Okay, it's when we start moving out from x where dy and delta y would differ. Remember, dy means we're using the tangent line. Delta y, that's the actual change in y on the curve. Okay. The closer we are to x, the closer dy and delta y will be to each other. Okay, so we are going to go back to that square root of 4 example, okay? And we're going to do it using this differentials model as opposed to writing an actual tangent line equation. Okay, so you can kind of see the difference. It's still the same concept, but it's just going to look different, right? So, go ahead and write this down. Let f of x equal radical x, at x is 4, and our change in x is 0.02. If delta x is 0.02, what is dx?
0.02.
Okay, good. Delta x and dx are the same thing. Okay. Now, when we talk about dy, remember we talked about how f prime of x equals dy over dx. So dy equals f prime of x dx. That will happen every time. Okay. Now, we already decided that the derivative was 1/2 x to the negative 1/2. Do you agree? Okay. So dy is our derivative evaluated at x times dx, which is 0.02. So 1/2 times 4 to the negative 1/2 is 1/4. Multiplied by 2 100ths. Is 0.005. That is our dy. Okay, so this is what that means. Since the square root of 4 is 2. Then the square root of 4 plus delta x is that y value plus dy. So the square root of 4.02 is approximately 2.005. That is what that means. Now, I'd like you to go ahead and get out your calculators. You're going to see how close this really is. When we talk about delta y, that is the actual change in our y values, which means what is the difference between the square root of 4.02 and the square root of 4? What is it? Okay. Are dy and delta y very, very close to each other? Yes. So this is a pretty darn good approximation because the actual value is 2.00499. Any questions? Okay. Go and write this example down, please. dy is f prime of x dx. Gina, what is f prime? Or in this case, y prime. Okay, so we can write dy equals 12x squared dx. We know that x is 2, excuse me, x is 1, and dx is 0.01. Essentially, we have 12 times 100, which means dy is 12/100. Okay. At your pod, talk about what this tells us. What does dy tell us about the graph? 1, 2, 3, go. What is f of 1? Okay, so what can this dy tell us? How can we use dy and the other information to to give us something about the graph. 5-4, you were having a pretty good discussion. Okay, so if f of 1 is 3, then what else can we write? Okay, what's our change in x? 0.01. So we have information about f of 1.01, and that is approximately 3.12. We add the delta x, we add the dx, we add the dy. We moved along our tangent line for an approximation. That's what we did. Isn't that nicer than writing a tangent line equation? It's giving me like nothing. It's the same thing from writing a tangent line equation. We just do things in a different order. Okay? Now, what we're going to do is use differentials to approximate the error in computation. So in this case, we're going to use differentials to approximate the error in computing the volume of a sphere. We know the radius, and we don't want an error larger than 0.2. Okay, so write down what you need to. I wouldn't write down every single word up there, but we're approximating the error of the volume when our radius is 10, and we don't want an error larger than 0.2 centimeters. Who remembers how to find the volume of a sphere? 4/3 pi r cubed. Okay, so instead of x and y, we have r and v. So instead of delta x, we're going to talk about delta r. What is delta r? 0.2. What? Oh, okay, thank you. Positive or negative 0.2. Okay. So then what we can do is we can write dv, that's like our dy, equals, what is the derivative of 4/3 pi r cubed?
3 pi r squared.
So we have our dy equals, so we have dy equals our derivative times dx. But instead of y, we have v. Instead of x, we have r. Okay? So, our radius is going to be, where is it, 10? And we decided our dr was plus or minus 0.2. Okay? We have 10 squared, which is 100, times 4, which is 400, times 0.2, which is 80. So we have 80 pi. The whole point of this is no calculator. But we will need your calculator, so get it back out. Okay? So this is how much our volume can differ by. If we want our radius to only differ by 0.2. Okay? Now, when we calculate error, what we're going to do is we're going to take that differential, how much can our volume differ by, over what the actual volume is. So our volume can differ by plus or minus 80 pi, and our actual volume at 10 centimeters would be 4/3 pi r cubed. What are you getting for us, Eric?
4188.79 is the denominator.
Okay, so take 80 pi divided by that.
Oh, so that was 0.06.
Which means we're going to have up to a 6% error. Which doesn't seem very big, right? But 80 pi seems like a big number. Okay, but in the grand scheme of things, if our radius differs by 0.02 centimeters, we're going to have up to a 6% error. Okay, your assignment, which is on your gold sheet, I have folded problems for you that are required. I would encourage you to do all of them, but I would just look to that for these problems.